Hi, everyone. No, no, no. Well, thank you all for coming to the afternoon part of our event. Well, my name is Jamie Yüksel, and it is my distinct pleasure to invite yet another distinguished alumni of Utah to the stage, Dr. Steve Parker, who is currently at NVIDIA as he's the Vice President of Professional Graphics, and he's been doing a lot of ray tracing related stuff, which is very dear to my heart, I have to say. Before that, though, before joining the NVIDIA 2008, Dr. Parker was actually here in Utah, or is a member of our faculty here. And before that, he had a PhD from Utah in 1999, if I remember correctly. So we're ready to hear from him, I guess. Thank you.
Well, thank you. So I'm here, and I'm to somewhat talk to the students, and so hopefully there's enough students here. There's others. Hopefully will at least be entertained along the journey. And I think they invited me so that I could assure everybody that the fun wasn't concentrated only in the 70s. So hopefully I can dispel that. So hopefully I can dispel that rumor, and let me tell you a little bit about my role at NVIDIA. So I joined NVIDIA just over 15 years ago as part of NVIDIA research, and over the course of that time frame, we built what is now known as NVIDIA RTX, or real-time ray tracing capabilities that ships in tens of millions, I don't know how many exactly, GPUs around the world, runs games, and brings what has traditionally been a high-end computer graphics experience to real-time, commodity, interactive gaming. And then the other role that I'm doing now is now trying to take that even further. And I'm the CTO of a product that we're building called Omniverse, which is kind of the gathering place for all of NVIDIA's technology. We bring ray tracing and physics and simulation of various kinds, and content creation and large language models and all of those things into a common, what we call the industrial metaverse. And Omniverse is one of the most ambitious projects I've ever been a part of, and you'll hear a little bit about it, see some cool pictures from it too. But that's what I do. It's a long journey and a passion project. I think the most important thing I want to say to all the students here today, and hopefully there are more watching online, you are absolutely, unequivocally standing on the shoulders of giants. Many of those giants are in the room today. There are many others that are not. And this photo is a little bit weird, a little bit slightly disturbing, but it illustrates both the amazing capabilities and the limitations of AI-generated art, right? So I told the AI, I said, please, I didn't say please, but I said, maybe that's the problem. I said, make me a photo of somebody standing on the shoulders of a giant who's standing on the shoulders of other giants, right? And because that's really how I feel like my time here and those that built the foundations on which I can extend and build, and hopefully I'm building foundations for others to extend and build in both a technical way and a very personal way too. So, so let me try to convince you of this in kind of three big topics. I'm going to talk to you about some of the giants in my life. I'm going to talk to you about kind of where that led me over the last decade or so, and we'll get into some technical tidbits a little bit, and then kind of look forward a little bit. Like, what is the future? Is it all done? Was all the fun in the 70s and 90s when I was there, or is there more fun to be had? And so hopefully I'll convince you that there's both some challenges and some fun. So, and there's many giants, you know, in a personal level of my life, you know, family, parents, students, colleagues, and you know, very grateful for all of them, hundreds of them, thousands of them. And they didn't allot me 45 days to go through all of that. But I want to point out, with the benefit of hindsight, I want to articulate 9 very specific moments that are almost like, you know, flashbulb events in my life, in my career, shortly before and shortly after Utah, that led me to where I am today, and hopefully draw what you can, you know, what you as a student or faculty can take away from that. So the very first one is, you know, what is the spark? How do you ignite a passion? I was interested in computer graphics since I was a teenager, watching, you know, the work of many of the people in this room. And I was an undergraduate student at the University of Oklahoma. I liked to wander through the library and look at the books, and I stumbled upon one book in particular that, out of all the books in the entire engineering library, ignited a passion. And in particular, chapters by Eric Haynes and Andrew Glassner. Eric Haynes is actually now on my team, but you know, that were written in a way that was approachable, that I could, you know, as that 21-year-old or however I was, that I could understand it, and I could be interested in it, and I could see that there was more potential to go further from there. And it turned that interest in computer graphics into a passion. I wrote software and things like that. I also paid a lot of overdue late fees for that book. I think probably bought it three or four times. But the next thing that I was inspired by as an undergraduate in Oklahoma is something that some of you may remember called the Utah Raster Toolkit. And it is there was no internet. There was, like, you know, this Usenet thing that was kind of hokey, but you know, there was no advertisement that I saw or billboard that I saw that said the University of Utah was good at computer graphics. That was the thing that connected me to the University of Utah. And I knew of Utah because I had family here. My parents were both born and raised here, and I, you know, my diapers were being changed when a lot of the foundational work was happening here. But that one thing, and the thing that I take away, or invite you to take away from that, is to build stuff. And you heard about the same thing earlier on the panel. You know, build stuff that's larger than you as an individual. And you know, it's subsequently been replaced by other more sophisticated things. But you know, I guess one other maybe takeaway more for the faculty is the fact that it was called the Utah Raster Toolkit as opposed to the Raster Toolkit was a brilliant branding move that led me to the University of Utah. And one day I was visiting my grandparents when they were still around. And I was like, okay, well, I want to go up to that university. I want to see what that is all about. Is it really, you know, more than just this little raster toolkit thing, or is it something? And it was summer, so none of the faculty were there, except for one, Jamie Painter. And Jamie dropped whatever he was doing and spent an hour with me and taught me something. Taught just, you know, as a teacher and a mentor. And I didn't write a specific advice here because there's so many things to do. I think, you know, making, you know, for the faculty, making time for a curious student that, you know, wandered in off the streets, or making, you know, the fact that I was either naive or brave enough to just, you know, wander into the department unannounced, and my experience with Jamie then, as well as knowing him at Utah and at Los Alamos, is that he was always teaching. In particular, the topic he taught me, and I remember it again like a flashbulb moment, is he taught me what a light expression was. He asked me if I'd heard of it, and he told me about it, and I was able to understand it, in that time period. And so I was able to take computer graphics courses from him. He was a great teacher. The next one you saw earlier, Dave Hanscom. So I was accepted to the master's program at Utah, and a little bit like some of the earlier stories, I came to get a master's, and then eventually got tricked or sold into getting a PhD, and there was this meeting, like all grad students have to be at this meeting, and you have to learn how to teach. Well, I wasn't offered a TA-ship. I didn't have the best grades or best track record, but I got in anyway, and there's this moment that is like a flashbulb moment that probably didn't mean anything to Dave at the time, but there was a bunch of students, and we all, if we're honest with ourselves, have a small dose of imposter syndrome, right? And so we go in, and I didn't know what that was called at the time, but you go in, and there's some other student, and they're giving we were invited to give I think a 3-minute lecture on a topic that we were well acquainted with, and that was supposed to give us and we got feedback on our teaching. Dave was able to provide, and the topic that I wanted I'm going to do ray tracing. I've been learning all about ray tracing the last 2 years from that book in the engineering library. And then somebody else did ray tracing. I don't know if I should do that, because he knew a lot more than I did, because I was this self-taught kind of person. And it's like, okay, but I like Dave came in with a handicap, which is called an electrical engineering degree, and so okay, well, I can do Carnot maps, right? I think it's easier to teach that in 3 minutes, and I can teach people how to do a Carnot map in 3 minutes. And so I did that, and little did I know, but Dave Hanscom was immediately said, I need him for my TA for my computer architecture class, which I TA'd for him my first year here. And that I came here to Utah without a job, small family, no job, and turned that one thing of just showing up and going with your gut was able to turn something where I wasn't even kind of sure how I would finish the first year of graduate school into something that gave me a golden opportunity to be on campus and to learn how to teach from one of the masters. Delighted to see Jim on the front row. So Jim, your son, Mike Clark, is another one of these flashbulb moments in my life. He was a really good friend, tremendous individual. What was that? He's and one of the things that he taught me is that group projects can actually be okay. I had in my entire undergraduate experience had never had a successful experience with a group project, but Mike and I kind of clicked and got it off and worked on compiler project together in John Carter's compiler class. And he's an excellent collaborator. Taught me a lot of things about Emacs, just basic things, and was a friend throughout my graduate career, and it was truly a pleasure to have that experience. Now the next pivotal moment is Chris Johnson. So after my first year of graduate school, I did well. I worked my tail off in all those classes. I worked my tail off for Dave and debugged all those suitcases for all the students in the lab, and then I talked with Chris, and he had this little dark, dingy office right next to the noisy, smelly, stinky bathroom in the Merrill Engineering Building. And he's like, well, I think you should come join my group. And I was like, well, I don't know, because Utah was in a, let's say, a rut of tenuring students or tenuring professors, and like, is Chris really going to be around, or is he going to, and I said, okay, well, maybe, and then he said, well, you need to get a PhD, and I said, oh, well, I was only just planning to get a master's, and then, work to support my family, and he convinced me that getting a PhD was worthwhile, and hand raised me as an academic and a collaborator for years. He sent me on my first business trip. He started me on 25 consecutive years of attending the Supercomputing conference, which was broken only by the pandemic. We spent a week in London. We've edited countless papers and learned how to write from him. Countless grant proposals, and most importantly, he pushed for the resources that we needed to have a unique research footprint. And he helped me apply for the Computational Science Graduate Fellowship from the Department of Energy, which reinforced the value of interdisciplinary work. It also gave me an opportunity to go work with Chuck Hansen and Jamie Painter again at Los Alamos. And it's also where I met my wife, so it worked out okay. And Chris was instrumental in achieving that. And so I was there with building the foundation of the Ski Institute. This is Ski Run. This is my project that was kind of one of the first kind of group projects that we got together as graduate students to go build. And what you saw on the surface is pretty pictures and visualizations, but what you missed was all the Chris editing papers and spending 24/7 writing grant proposals or trying to work the politics, and occasionally getting arrows in the back in the process. But it did work out. And one of the things that I think is in common with the period that we had with the 70s is we had resources that were pretty unique among the academic department. We had a lot of SGI equipment. We had indies and octanes on our desks. We had a big thing called a reality monster, which filled half of the machine room, and we wanted to call it Raptor, but then we split it into two pieces, and so we called it Raptor and Rapture, and that caused no end of confusion. But because this thing was sitting there, like, well, what can that thing do? Like, it's supposed to be for this, computational science stuff we're doing, but I'm pretty sure, we can use all the CPUs in there for some computer graphics. And that's begins my engagement with who I think is the ideal collaborator, Pete Shirley. Pete is an idea factory. He'll spin things out. He has a little bit of a contrarian attitude, and that's probably my takeaway for each of you, is to be slightly contrarian. And he pushed me to publish the things that we were doing. And he's always upbeat and always positive. And what we did is we built something called a real-time ray tracer using that SGI equipment. And that real-time ray tracer at the time was an oxymoron. And we took all of the models that were created in Utah in the 70s, and we built interactive, crude, real-time experiences. And we also found that we could take that thing and use it for scientific visualization. We're able to beat the standard marching cubes and other techniques by orders of magnitude. And so it turned something from, kind of an experiment for fun into something that was suddenly practical, and that won the Best Paper Award in Viz 98. We'll tell you a little bit more about that because it kind of led to where I am today. The other flashbulb kind of moment is the CSAFE project. It was led by Dave Pershing, and it's called the Center for Simulation of Accidental Fires and Explosions, where the goal was to build a simulation of a puddle of jet fuel that's you simulate all the chemical reactions and fluid dynamics in the fire that and over which you suspend a steel container filled with a high-energy explosive, and you simulate all the dynamics in that entire event. It was a super ambitious project. I think if we'd known how ambitious it was at the beginning, we may not have ever started. That's how all the best projects begin. It lasted over a decade. I was there for a decade, but I think it went further in other forms beyond that. And Dave was a very firm but gentle leader that is a style that I continue to try to learn from today. And again, we had access to more hardware. It was at the DOE labs, but there were these ASCII computers that was the first petaflop machine, and the ASCII white was, I can't read it from here, 12 teraflops. And I just want to put that in perspective. I forgot to put the date on ASCII purple, but where we're at today, so a single NVIDIA GPU that's about this big and runs 300 watts is either just slower or just faster, depending on how you count it, than that ASCII purple. ASCII purple was $300 million, multiple megawatts, and filled a room, and took a fleet of personnel to manage. And there's some things that are weaker about and there's some things that are stronger. In particular, it's got 10 times as much floating point horsepower if you're doing AI type work. And so we'll get back to that, how we've done this. But the thing that I think all the students should be aware of is that throughout its history, Utah has always punched above its weight class. Why is it that this fairly small university at the time in this very small state, approximately hundreds of miles from anywhere, why is it that they're always named in the same sentences as other places that are much more common? And so there's obviously all the foundational technologies that I think the rest of this is about. There's the Science and Technology Center, which was Brown, Caltech, Cornell, UNC, and Utah. We were the first, one of the first 4 nodes on the ARPANET, which became the internet. The ASCII Center that we talked about before was Caltech, Chicago, Illinois, Stanford, and Utah. And punching above your weight class is a little bit of a angry analogy, but I couldn't come up with a better one, right? And so, I think above all, I hope that continues. But the close of my University of Utah came one day on a day, with weather similar to this, where David Kirk and David Lubke flew into town and said, what, we're starting this NVIDIA research group, and we kind of like you to, come, do some, start some ray tracing work here at NVIDIA. And they said, well, what do you want to do? And I said, well, I think I would really like to build an engine with ray tracing as the focus. I think it will, it will be able to be useful for a lot of things. And luckily, and by the way, I told them it would take 5 years, but luckily I found fellow travelers and people who are already starting on that project at NVIDIA. I worked very closely with Rev Leberedian, who started Omniverse, and so rather than me starting a competitor, I joined his team. Right, I joined forces with him to go help build that, and so we build the rendering system and some of the parallel distributed computing pieces of Omniverse. So the next chapter is, what did we do to make real-time ray tracing real? Well, in 1980, ray tracing was proposed, and in one of the more seminal papers in all of computer graphics history by Turner Whitted. And around that time frame, Turner was asked, what would it take to make this real time? And this was his response. And I'm paraphrasing. He told it to me personally, so I'm just kind of going from memory. But he said, well, you go take a bunch of crays in the desert, and you put a red, green, and blue light bulb. And it had to be a light bulb because the blue LED had not even been invented yet, right? So tie a red, green, and blue light bulb to the top of each one and fly over it at 30,000 feet. He's a pilot, And that was his proposed solution. So remember that, because we're gonna get back to that. So I mentioned some of the work that we had done with Pete about interactive ray tracing. We started publishing it. How do we use this big SGI the size of a room to go do that? We used even larger ones at SGI and at NASA. We took models, all the famous work that had been done decades before, and produced these real-time systems. And then when I joined NVIDIA, we were like, well, let's figure out how to make that work on a GPU. And we produced a demo. This is now a decade or 15 years old, but in about 1 month, produced a demo of that where we had a car running, and it looks a little bit flat and stale by modern graphic standards, but at the time it was. At the time, the common wisdom was, GPUs will never be good at ray tracing, and so we set out to prove them wrong, and then subsequently turned that into a stream of products and more demos, and kept raising the bar. And it was published in SIGGRAPH of 2010. The programming model subsequently republished an extended version of it in CACM Research Highlights. And the foundation of this programming model are now the guts of DirectX ray tracing and the Vulkan ray tracing standards in the industry today. We also kept working on making it more and more realistic. One of these photos is one of these is a photograph, and one of them is simulated, path traced. So we had a real or rendered contest around that time frame to see if you could guess which was which. It was super popular. I have actually forgotten which one is which, and I'd have to stare at it a little bit to know. But it's you have to treat this thing as a science. Get all the calibration and the entire units correct and pipeline things. And the core of it is the core of ray tracing is how do you find the needle in a haystack, right? So I have a point and a line, and I want to know what is the triangle that is most closely visible along that line. The most common technique is called a BVH algorithm, where you kind of think of, I have a box, and in that are other boxes, and in that are other boxes, and then in there is finally the triangle that I want. And so on a GPU, this runs on our SM, our streaming multiprocessor, and it runs pretty efficiently. You can do this, but the challenge is many thousands of instructions per array. And so what Telly Whitney described as a special purpose processor, what we did was put a special purpose processor in the special purpose processor. And that's what we call RTX, or the RT cores, where we took the core of that algorithm and built very focused hardware to do what was 80% of the work, and built fixed function hardware that works in conjunction with the streaming multiprocessors on the device. And one of the funnest moments of my life, stressful but also fun, is at SIGGRAPH in 2018. We announced this when we launched our product line called Turing, which we had been able to keep secret for 5 years that we were working on this. And we built a physical mock-up of the Turner-Whitted glass ball checkerboard scene and invited people to come take pictures of it. If you look closely, the middle one's Don Greenberg and Andy Van Dam. And I have a picture of me with Turner-Whitted in there, but unfortunately it's buried somewhere in my millions of photos. And we launched this to the world, and the world initially didn't get it, but now they do. So there's one other thing that we looked at when we first started doing this is so this is a visualization we made where it's how long does it take? Instead of showing the picture, it's how long did it take to trace the ray in that pixel. The brighter the color, the longer it took. And this was a problem because the ratio between these things is like 100 to 1, right? And so if you've taken a parallel computer science class, you've been told that ray tracing is embarrassingly parallel, so simple. But when you start putting load balancers and all the data structures and other stuff on this, it's not an embarrassingly parallel problem anymore, right? If you actually try to make it real. And so in last fall, we announced the second major thing that we had been working on, which is something called shader execution reordering. And you can think of it as adopting the techniques that have been built for out of order processing in an instruction stream to ray tracing, where we will sort and bin like for like. And so if you're all the rays that are hitting the shiny part or the car paint or the wood will all be regrouped dynamically in the chip on the fly so that it can keep up with the pace of increase. And the good news is, we've decided to continue to do more, but I'm not allowed to tell you about it right now. But let's revisit what we heard Turner Whitted say. Like, what if you just took a bunch of crays in the desert and put them in the desert? Well, cray 1 was 160 megaflops, and the GPU that we're delivering this stuff on is either 83 teraflops or 191 if you count the ray tracing horsepower. And it's about 500,000 to 1.2 million. And so, but we can do 8 megapixel image. So there's roughly a factor of 8 missing in there somewhere. So he was pretty close, but there is one more factor of 8, and that's where AI comes in. And so the thing that makes this viable is something that we call DLSS, or deep learning supersampling, where it takes those 1.2 million pixels, and what the images that we show, 7 out of 8 of them are hallucinated by a neural network. And so, Shannon lied to you, right? There is more information in there. And it's not that he lied, he just had the wrong problem statement for the problem that we are trying to solve. And it's not how much information is in a signal, it's also about the information in your experience, right? And that's really what a neural network is doing, is encoding that experience in numbers and other information. And that, cars tend to look like cars and people tend to look like people. And so that boosts something that's borderline impractical to now something that's practical. And so I'm actually amazed that if you take the cray 1 and where we're at today, and you include not only the raw floating point and a factor of 8, it's it's at least 1 decimal point, maybe 2 or 3 from what Turner's somewhat flippant projection. So we've continued to push on that. There's working very closely with NVIDIA Research, other Utah alum, Chris Wyman and Aaron LaFawn, who leads our real-time graphics. We've taken these images that were previously minutes to render. They're now 10 milliseconds with thousands of lights and hair, dynamically simulated hair on the tiger and things like that. And it's, by crafting every single level of the hardware and software that we're able to get there. Turner, these images are arguably much more sophisticated than Turner Whitted's original pictures, but we've also had algorithmic sophistication that's increased along the way. It's not just the hardware that got us there. All right, now I need to know how to go forward. So we've taken those raw capabilities, built them into a system called Omniverse, and we've use Omniverse to build things like virtual avatars. This is our Toy Jensen is what we call CEO of NVIDIA, TJ for short, and there's all sorts of AI in there that can take audio and distort the mesh so it looks like it's talking, that can have a natural language response like ChatGPT that was referenced earlier, and the graphics and the physics and all of those things embedded together. And there's no, we do our very best to have no phenomenological graphics, but to really do simulation and AI enhancements of that simulation. And so what do you do with, when you have all of that computing power in a small piece? Well, what you do is you build bigger ones out of it. And so we announced this just last week. This is a 512 GPU data center product called OVX. And we are building a product called Omniverse Cloud. So this system has over 100 million way parallelism. And so, the multi-processing that we talked about earlier is where that all began, but it's gone a lot further than that. And one of the things we're doing with this is BMW is building a factory entirely in Omniverse years before they will build it physically, a couple of years. And they estimate that it will save them 30% of the cost of this multi-billion-dollar factory. And and we simulate all the robots, we simulate all the processes that are going through the factory. The factory is so large that the curvature of the Earth matters. And so we built Omniverse to be able to handle the complexity, and the physical simulation basis of it is what enables us to do that. So if you want to sell them a robot that sweeps the floors, you can go prove out whether your robot is going to work in this virtual environment without injecting it into the real factory and potentially causing expensive delays in the product line. And so we're taking those pieces now, building larger and larger and larger amounts of parallelism that we're building in Omniverse Cloud, which is more and more parallel. And I think the best way to highlight what we've been doing is just to show you some pretty pictures, since it's a graphics conference after all. see it again. So there's, it's giants standing on top of giants, right? That led to this point. And what's next? I think there's kind of two opposing truths that everybody needs to have in their mind. Number one, the pace of Moore's law has either slowed or stopped, depending on how you calculate it. But the pace of computing will continue to accelerate. And why? How can those two things be true simultaneously? And I'm running short on time, so I'm not going to go into too much detail. But Moore's law was always an easy target for colloquium talks, and so I'm vowed to never, to never give one myself. This is my favorite quote. If you were plowing a field, would you rather use 2 strong oxen or 1024 chickens? Well, it turns out the chickens won, but the shape of Moore's law has shifted, and starting in the late 2010s, what was known as Dennard scaling ended, and began multi-core and special purpose processors, and rapidly increase in parallelism. Densities continue to shrink, but costs don't. And actually, only 2 or 3 years ago, projections about what the iPhone costs, the cost per transistor is actually not going down. And so, so what that means is, business models will shift and technologies will shift. And by the way, it's not for lack of trying. If you haven't seen this was announced last week in our keynote. But we're working with ASML to work on extreme ultraviolet lithography, and there's some, all the transistors are called polygons, and so all of the same algorithms we've been talking about earlier to make beautiful pictures also apply here too, and this is an incredible machine. I'll skip some of the videos in the interest of time, but it produces, it vaporizes tin with a pair of lasers to produce an exactly 13.5 nanometer pulse of light that is used from the masks. And what they're printing is much smaller than 13.5 nanometers, and so they have to solve the interference patterns that will produce the transistors at the end of the day. You can have one of your own for $250 million, and we're working closely to use AI and accelerated computing to help make that better. But the appetite for computing continues to grow. It's estimated that the global data center uses about 4% of the planet's power, and is continuing to grow. ChatGPT popularity has been through the roof, and their CEO was quoted as saying the costs of inferencing ChatGPT are eye-watering, I think is the term he used. And so that leads me to 3 opportunities. One is, for all of the students in the room, interdisciplinary computing. The advances in computing will come from understanding the entire stack, will come from algorithms and parallel algorithms. We've created new algorithms for sorting in the last few years. We've cracked algorithms that were previously thought to be serial. We now have parallel equivalents of. And connections to all the other disciplines, science, language, art, engineering, business, and you name it. I'm going to not talk about the specific parallel algorithm we cracked. Architecture, we've already talked about the need for special purpose architecture. And then, of course, it wouldn't be complete without a nod to AI. Every chapter of every graphics book that has ever been written will need to be rewritten because there will be some component in there that will be AI enhanced. Texture, or how you even create the textures, or how you look them up, or the the supersampling work or denoising work that we've done. And it's what I call the tension between good and evil. So like, what is the graphics of the future? Is it just AI, or is it some physics core that's enhanced by AI? And I don't know. Like, for the first time in computer graphics, that I've been in computer graphics, it's not a linear extrapolation of the present. These are some of the ways we think about it. What a rendering algorithm is going to do is not generate pixels. It's going to generate something that an AI can use to generate pixels. And what that means is that you're trying to maximize the diversity of information in that footprint so that AI can reconstruct that. And so things like coherence and things like that are not as easy to find. It's still there, but not as easy to find. And so my conclusion is there's never been a more exciting time in the history of computer graphics, because I think the revolution that's happening now, like computer graphics will improve because of connections to language models like ChatGPT. And the revolution that's happening now is just as profound as the revolution that we are here to celebrate today. The School of Computing recognized that in the year 2000 when they changed the name to the School of Computing. I argue it was a very prescient change driven by Tom Henderson, as you heard earlier. And I'll point out that this was 7 years before the iPhone was even announced. And it was a recognition that computing was playing a broader role in many disciplines. And I'm not talking about, I use a spreadsheet to track my legal documents, right? But deep algorithmic innovation in banking, in languages, even psychology, and School of Computing provided a fertile ground for that, for the Ski Institute and CSAFE and other interdisciplinary engagements. And I guess I have to make sure that everybody knows, like, this needs to expand even further. So out there's some brochures of how we can all help contribute to the future of the University of Utah Computer Science Department, and let it grow and expand to include all of the disciplines in computing, but also the engagements with literally the entire economy of the planet. There's 3 pieces of advice for the faculty and staff. Please help keep punching above the weight class. I appreciate those that gave me a chance. Chris, whoever got me, whoever admitted me into the program in the first place, and keep the hands-on spirit alive. For the students, I'd also, demand or push it to be a special place. Chase both depth and breadth. The depth that you get here will get you your first job, but the breadth will get you your second, third, fourth, and fifth jobs. Embrace parallelism, whether you are thinking about it every day or not. That's right now the only way forward until quantum computing becomes a reality. Build something ambitious, something that's bigger than yourself. And that was a tough step for me to take, but something that has rewarded me greatly. And then finally, respect that you're standing on the shoulders of giants. And with that, I will leave it with what ChatGPT thinks of the University of Utah. So. Yeah, Jim.
I'm just concerned, that thing with the waves?
Uh-huh.
That was a lot of physics and modeling and also a lot of rendering. How much, on the rendering side, was that done in real time?
I actually can't remember on that one, but we do have a lot of them that are real time, yes.
Yeah, I'm just wondering the ones that are super high quality. Trying to get an understanding of the power used.
Oh, the power used? Well, so
You mentioned teraflops.
it uses, there's no question it uses a lot of power, but I think the missing thing is about efficiency. right? NVIDIA has a consistent track record of being atop of the green 500, not because of, they use a lot of power, but they have a lot of flops per watt.
NVIDIA's I own nothing but NVIDIA.
Okay,
That's
well,
how
that's
much
good
I
to
love
hear.
NVIDIA.
But
in stock.
Okay.
Yeah.
Really, because Dennard scaling, the performance is power efficiency.
I really am concerned what your thoughts are regarding power reduction. I'd like to know, get your fastest, most beautiful rendering thing in the world.
Yeah.
How much power does it use in a 60th of a second?
Well,
Take any of that.
Sure.
Just tell me the power used in a 60th of a second.
I can't do the conversion to joules in my head, but
I will tell you
yes.
that is your most important number because
I
you
agree
got to
with
get
you.
it to real time.
Yeah, but we do it perf per watt, right, instead of in joules. But perf per watt is our number one challenge, no question, because power is constrained everywhere in your phone, in your laptop, even in the data center. Power is the very first conversation we have. They're out of power, right? Where can we plug one of these things in?
You probably use a huge amount of power.
And what we're focusing on is amortization, right? So what you see and what I see are different, but there's a lot that's also the same. And so if we can amortize and share, then it makes a more efficient.
What do you mean amortization? Tell me explicitly what are you referring to? Not making an average of cash return or what?
No.
And what you're doing has to do, because I'm confused, okay?
Well, okay, so amortization of viewpoint.
Of what?
Amortization of what you see from a specific point of view, right? And so if we're looking at each other, but if we both look this way, all of the complexity out there doesn't look that different for you and me, right?
You want to just do computation where you need it.
Correct.
That's one good way to do it.
Yeah. And so lazy evaluation, amortizing between multiple people, multiple viewpoints. We use a lot of neural networks to decide where to go.
You do a great job on that, I think. Excellent.
Yeah. So it's a problem that's never done, right?
Yeah.
In order to reach the next level, we have to drive down power, and maybe that's what the next generation will conquer. So
I think your idea about parallelism is obvious, but I think all of the innovation, what I'm going to say a little about. Well, by the way, people don't know it, but I have to leave. And I'm giving a 15-minute talk at 3 here. Yeah. So, but I'm just curious about, the parallelism idea, the architecture, which is sort of what I've been thinking about since I talked to Bob Sproul. But seriously, it's the key.
Yep.
It was the key to everything I did when I was in graphics.
Exactly. Yep.
And anyway. One of the giants for sure that we have stood on in this endeavor. I think what we've learned is that there is no silver bullet, right? That there's not just one dimension of parallelism. There's layer after layer after layer of parallelism, and that there's not one power-saving thing, but there's combinations and permutations of techniques. The energy savings is going to come from parallelism, believe it or not. But anyway, that's just
I agree with you there. Yeah.
And energy savings to me is right now the biggest issue.
It is the biggest issue.
You can't spend I don't know how many gigawatts you even use to make. But if you're going to do it, whatever it is, you're going to use a lot of them, and you do it in 30 seconds.
Yep. All right. Thanks.